Good evening. My name is Jacob Bowen. This is my presentation of Introduction to Lift and Thrust for Professor Cunnington's class 3530 Intro to Aerodynamics. Let's start. The basic theory of flight comes down to a few simple principles. There is no definitive, easy way to describe what makes an airplane fly or why it flies in the most simplest of terms, but we can pare it down a little bit and make it slightly easier to understand for those who are just learning. Bernoulli and Isaac Newton, two very, very smart mathematicians and physicists, helped come up with a few laws that explain the basics of flights for forces: weight, lift, drag, and thrust, each of which opposing one another, but also working together to create a very simple balance that is quite cool when you actually apply it to airplanes and watch them fly. So first we'll talk about Bernoulli's principle, which is pared down into a simple formula, which is P plus 1/2 of rho times V, rho times V squared, which is the constant energy, or the sorry, not the energy conserved through this high and low pressure, high speed and low speed fluid dynamic cycle. The image on the right of the screen here is a Venturi tube, and it measures the velocity of a fluid moving through a standard sized piece of tubing until it gets to a narrowing in the tubing before then being allowed to expand out back again, or the A, B, and C sections in this tube. The A section is a wide opening with a constant velocity, constant pressure. B, the tube itself narrows down, which creates a loss of fluid pressure. However, the velocity increases to allow the same amount of fluid through that section of pipe as through the A section of pipe, before entering the C section of pipe, where once again it returns to the standard velocity and pressure seen at the opening of the pipe, which we can then apply to a wing. Is kind of a different shaped Venturi tube. Air hits the leading edge of the wing and is split over the two surfaces of the wing. The flatter lower section on the bottom here, and the upper curved camber of the wing, which acts as the narrowing in our Venturi tube. So as that air is forced up, the same amount of air has to travel over the top of the wing as traveling under this wing, creating a relatively low pressure on the upper section of the wing, on the upper part of the wing, and a relatively higher pressure section under the wing, which in a very, very basic sense draws the wing up into the air. The higher pressure is pushing up, the lower pressure is kind of sort of sucking the wing up into that vacuum that's left there. This is very, very basic of how fluid dynamics works and the conservation of mass, conservation of energy in fluid dynamics, but it's a relatively simple way to understand how lift is generated. Then are Newton's laws. Newton made 3 laws. The first law is the law of inertia, and it describes that any object at rest stay at rest. Any object in motion will stay in motion, until an outside force acts upon that object and either introduces that initial push needed to get an object moving, or introduces that stopping force needed to slow an object down and bring it to rest. Second law we have is the law of acceleration. The law of acceleration tells us basically that the acceleration of an object is basically directly proportional to the force applied to it, and inversely proportional to the mass of the object itself. So the force needed to move a 20-pound weight is 20 pounds or greater. Basically meaning you need the object weight or more to move the object, and then vice versa, you need the object's weight or more over a distance or time to stop an object. And then finally is the law of action and reaction, Newton's third law. Any force applied to an object with mass, of course, any force applied to an object is proportionally reflected back. So the force needed to move an object, to push an object, is basically proportionally or directly reflected back the opposite direction. So if you push on an airplane, you also feel that force pushing against you. So how are these applied to an airplane? Well, Newton's first law and second law are almost directly related to thrust and drag. Drag, which we'll cover later. Thrust we'll cover a little bit sooner. Newton's first law basically directly relates to the thrust required to move an airplane. You need a direct force applied to that aircraft. If you don't apply thrust, the aircraft's not going to go anywhere. It's basically just going to stay at rest. And then the second law, same thing a little bit, describes it a little bit further. So instead of just basically needing to apply thrust, it describes that you need a specific amount of thrust to move an aircraft of a certain weight. And without that thrust, the plane's not going to go anywhere. And without enough thrust, even, the airplane won't be moving fast enough for the wings to generate lift. Bernoulli's third law and Bernoulli's principle, and Newton's third law to work together to generate enough thrust, and then generate enough lift and pushing force on the aircraft to actually allow it to fly, which brings us directly into Newton's third law, the law of action and reaction, which works very close in tandem with Bernoulli's principle to describe how lift is generated. People argue to this day whether one or the other describes it better or more accurately, and that's still a pretty even debate. But anyway, Newton's third law, as it relates to lift and the forces acting upon an aircraft, Newton's basically say that the amount of air impacting the lower surface of a wing, the flatter undersurface of that wing, is deflected downwards. But because of the law of action and reaction, that same amount of air is also being pushing up on the wing. So not only is it being deflected down by the wing, but that same force is being applied to the underside of the wing, which is pushing that wing up into the air. Which kind of gets us to my point of view on whose law describes lift better. It depends on the phase of flight. Newton's law more so deals with slow flight, slow airspeed, high angle of attack to generate that lift. You're more so relying on the air being displaced by the wing to keep the wing in the air, keep the plane in the air, keep the wing generating lift. As you get to flatter, higher speed flight configurations, that changes a little bit to, well, now you have a super low pressure zone over the top of the wing and a relatively high pressure zone under the wing, which is actually then just sucking that wing up into the air. But again, neither one is more right than the other. And on the subject of lift, lift can be broken down into this equation: F equals CL times 1/2 rho V squared times S. F obviously is the total amount of lift generated by this equation, calculated out by this equation. CL is the coefficient of lift, or also called the angle of attack of the wing. Rho is going to be the air density, same as it was in Bernoulli's principle. V, same as Bernoulli's principle again, is velocity. And then S is the surface area of the wing. As pilots, we ourselves only deal with, or can only directly control, the coefficient of lift, or the angle of attack of a wing, and the velocity at which the wing is traveling through the air. The surface area of the wing is something that's dictated from the manufacturer. If you buy a Cessna 172, you're not really going to make the wing on the Cessna 172 bigger, unless you're using flaps, of course. So we kind of control that in a sense, but controlling that wing surface area also changes the coefficient of lift, or the angle of attack of the wing. So it's more of a 6 of one, half a dozen the other in that scenario. Air density is directly related to the weather. So changing the angle of attack, changing the speed at which we are pushing the air, or the wing through the air, are all we have at our disposal all the time. If you take the example of a 2,000-pound airplane, in order to stay in straight level flight, that airplane, that wing, is generating 2,000 pounds of lift. If you change the angle of attack of the wing, so you slow the plane down, increase the angle of attack, you're still generating 2,000 pounds of lift to maintain the same level of flight. However, instead of relying on majority velocity, or about an equal percentage velocity and angle of attack, you're using the angle of attack and the surface area of the available wing to generate more of that thrust than the velocity, and vice versa. If you ram the throttle's firewall and pitch the nose down, you're relying less on angle of attack. The angle of attack relative to the wind doesn't matter as much, because you are going at an increased airspeed to generate that same amount of lift, and you can then generate excess amounts of lift, which then allow you to climb or descend. Angle of attack is directly related to how we stall an airplane. There's a common idea that airplanes need to always be going a certain speed in order to stall. That's not necessarily true. Wings can stall at a high airspeed if there is a high angle of attack. Angle of attack just describes the relative airflow over the surface of a wing, or to the surface of the wing, compared to the chord line of that wing. In straight level flight, or even slow flight, you still have a relatively smooth airflow over the surface, the top surface of the wing. However, if you increase the angle of attack without either increasing the velocity that the wind is hitting that wing, um, or without applying flaps or anything to increase the camber of the wing, decrease the angle at which the air is hitting the chord line. You get a high angle of attack situation where the the air going over the top of the wing surface is no longer smoothly attached to the wing. It's starting to separate towards the back of the wing, towards the rear edge, and it is disrupting the airflow and is reducing the amount of lift that's generated. There's no longer a laminar flow, which is just the smooth connected flow of the air to the top surface of the wing. If it gets bad enough, that turbulence that starts to form can actually creep forward and cause a stall all the way up the surface of the wing. Or if you increase angle of attack even further, the angle of attack is so high that the relative wind cannot form a smooth path over the top of the wing, and it becomes turbulent all the way down, and that is a complete and total loss of lift in that situation. The wing is no longer generating enough lift to keep the plane in the air, which is what we call a stall. As we said, culprit of a stall is the AOA, is the angle of attack. You need to be very aware of how a stall can form, and what can make a stall worse. You're most vulnerable in your low, slow states like takeoff or landing, because the airplane is already going slow. Too much of an increase of an angle of attack, too much increase in that chord line to the angle the relative wind is hitting the wing means that you're going to lose laminar flow over the top of the wing and maybe even have a complete airflow separation, causing a stall in a takeoff or landing phase, which can prove to be fatal. Meaning you have to be very, very aware of what a stall feels like, how mushy the controls get, what the buffeting feels like, and even being aware of the stall horn, so you can correct for that high AOA as soon as it develops and not once it's too late. Stalls themselves happen in a pretty specific pattern every time they occur, due to how air flows over the entire airframe, not just the wing. A stall will generally occur first here at the wing root, where there is a change in airflow direction, and where the wing is a little bit thicker and easier to disrupt. Air will separate here at the wing root first, and then that turbulent air here at the wing root will then quote-unquote poison the rest of the air along the wing until the entire wing has stalled, all the way to the tip of the wing. Stall strips and different wingtip designs have been implemented on more modern aircraft to try and stop this from happening, as it's a very dangerous thing. Stalls are something not to be light with. They're always to be taken very seriously. Stall strips right here on the leading edge of the DA-40 just help extend that chord line ever so slightly at that wing root to try and keep laminar flow, that sticky connection of airflow to the top of the wing at the wing root as long as possible. And then also, planes have started developing more glider-like wingtips that curve up more like airliners use. These help keep airflow attached to the top of the wing, also reduce also reduce induced drag at the tip of the wing, helping the wing generate as much lift for as long as possible before a stall fully takes place. It's easier to recover from a stall if at least one part of the wing is constantly generating lift, is a constant source of lift. Next is thrust. Thrust is a constant force. It must always be applied for an airplane to stay in flight, some form of forward momentum. In airplanes, powered aircraft, this is generated by an engine. Thrust is the source of movement, that source of inertia for Newton's first law to take place, to overcome that weight of an airplane, and then also that second law that Newton has, that law of acceleration, helps the plane accelerate and overcome its weight, or helps the plane accelerate to a speed in which the wings of the plane can overcome its weight and generate lift, and then also overcome the drag created by the body of the airframe itself, as well as the lift generated by an airframe will also generate drag. There are four main general types of engines. The propeller engine, which is one single engine piston aircraft, the piston-driven propeller engine. The turbojet, which is the oldest form of turbine-powered propulsion that we have. The turboprop, which is a mixture of the turbojet engine with the piston propeller powered aircraft generation of power. And then the turbofan, which is the newer version of the turbojet, a little bit more efficient. We'll go over that in just a second. Each engine obviously has its upsides, its downsides, its use cases, and what it can and cannot do. Propeller engines, piston propeller engines, are the oldest kind of engine that is seen in aviation. They are the original things that the Wright brothers used to power their aircraft, the Kitty Hawk and its first flight. They are internal combustion four-stroke engines, almost identical in design to what you see in the car that you may drive to work every day, or in the engine that the bus uses, depending on what form of transportation you take. Four strokes being intake, compression, combustion, and exhaust. The engine itself is attached to a drive shaft. That drive shaft can then be either directly connected to the propeller at the front of the engine, directly driving that propeller, or direct drive, or it is connected to a reduction gearbox for really high RPM engines, so that way the propeller is not spinning at the same high RPM that the engine is spinning at, and it doesn't create any issues there. Next is the turbojet. Turbojets, like I said, are the original jet engine design seen on aircraft. They use turbojets, and all turbine engines use a similar concept to the four-stroke combustion engine, except instead of having pistons that are moving up and down and up and down and up and down, to have that intake, compression, combustion, exhaust phase, the turbojet engine intakes air at the front of the engine, where it's passed through a compressor. The compressor here seen in this one is called an axial flow compressor, where it's made up of a set of rotors and stators. The compressed air is then passed into the combustion chamber, and then past the turbine fans, which are another similar set of rotors and stators, out the exhaust nozzle at the end of the engine, which produces that thrust. In the combustion chamber of the engine, initially for startup, a spark plug is active. to ignite the fuel-air mixture and help send it and pass it along. Once the engine is up to speed, however, there's enough heat generated in the combustion chamber. The spark plug's no longer needed. The engine itself is self-sustaining and generates its own combustion force. Next in that chain is the turboprop. The turboprop engine is, like I said, a mix between your turbojet engine and your piston propeller engine. The turboprop engine uses turbojet turbine internals, except instead of being a straight pass-through, we'll have exhaust nozzles that are not just straight out the rear, and is either directly attached to a propeller through a gearbox, or the propeller itself is separated from the engine, and there is a rotor-like impeller attached to the back of the propeller called a fluid couple, whereas the engine and it'll have a rear-mounted turbojet engine, whereas the engine spins up, the exhaust gases from the engine spinning up and generating thrust spin that propeller. Turboprops, like piston propellers, are good at relatively low airspeed, low altitude flights. However, they're faster than basic piston propeller engines and are capable of carrying greater weights and going farther. Turbojets themselves have the issue of being inefficient at low altitudes and relatively low airspeeds. They are great at high altitude, high airspeed flight. It's where they're the most efficient and the most cost effective. So that is where the invention of the turboprop comes into play. Finally is the turbofan engine. It's the most modern version of the turbine engine. It's the most recent iteration and what we're still developing to this day to make quieter, faster, more efficient versions of. It uses the same turbojet internals of a compressor section, combustion section, turbine section, and nozzle. However, that is shrouded in what's called a shrouded area. It's shrouded in a larger engine cowling with a shrouded fan attached to the front of it. The shrouded fan, in this case, moves bypass air around the combustion section of the engine. And that bypass air in more modern airliners, that application actually produces a majority of the thrust that a turbofan engine, that turbine is making, and the standard turbojet section, the standard turbine internals, are really there to power that fan and keep it spinning. The fan itself is attached to the front of the turbine engine via a reduction gear. The reduction gear allows the turbine internals to spin at a higher RPM than the fan, so that way the turbine can spin at its optimal speed and the fan can spin at its optimal speed without either one having to sacrifice a whole lot in terms of their effectiveness. The turbofan was invented due to a need for turbine engines that were easier, more efficient, more cost-effective to operate at those lower altitudes for longer periods as more air traffic takes to the skies. They are more efficient than your standard turbojet engine, and for the same engine size, they develop more thrust, meaning they can carry greater loads, go further distances, being more efficient. They generate the same amount of thrust as an engine larger than it is a very powerful thing. Obviously, these engines are used to generate thrust, which counteract drag. Drag is the opposing force to thrust, much like weight is the opposing force to lift. Um, Induced drag and parasitic drag are the two main types of drag that affect an airframe, and it is a pain for designers all around the world trying to design aircraft how to try and overcome these two types of drag. It doesn't matter what plane it is, how well it's designed, it will generate drag of some kind in some way. Induced drag is caused by the disruption of airflow, where two differential pressures meet. Most of the time, this is in the form of wingtip vortices. And then parasitic drag is caused by the body of the plane itself, as a byproduct of the fact that an airplane is a physical thing that's traveling through the massive fluid dynamics that we call the air around us. First, we'll start with induced drag. Induced drag is created by differential pressure. As air travels faster over the top surface of the wing, it is a lower pressure than the air traveling on the bottom surface of the wing, which is higher pressure. As they meet, they sort of slam together and spiral off the wingtips of an aircraft. They meet a bit more smoothly at the back edge of a wing in the middle, but on the wingtips they're kind of just forced together right here, and they create a spiral of low and high pressure until they're able to equalize some distance off the back of the aircraft. This creates an effect similar to a parachute. It's very disruptive to airplanes and brings them back. It actually brings back the coefficient of lift, so the plane is generally makes lift more in a backwards orientation, just due to how hard induced drag pulls on an aircraft. Induced drag itself is increased as an aircraft goes quicker, other way around, is increased as an aircraft goes slower, is sort of reduced the faster a plane goes, as that air coming off the wingtips doesn't create as much of an effect. It's more equalized quicker. Parasite drag is broken down into a few more categories than induced drag. There is form drag, which is drag that is generated specifically by the shape of the aircraft itself. The more blockier an aircraft is, the more sharp edges and things that wind has to impact with, the more drag that section creates, which is why aircraft designers use things like wheel pants and fairings to cover where parts meet and make smoother transitions between top of the airframe and underside of the wing, or top of the cabin and underside of the wing, just to try and reduce this form drag. Friction drag is the next form of drag. It's generated by the surface of an aircraft wing. The smoother, more waxed the surface is, the less friction drag there will be. Also, any of these little rivets or things that stick out also cause that friction drag. They're just tiny imperfections on the skin of an aircraft that drag that aircraft back. And finally is interference drag, which is a step off from form drag, where any 2 points on an aircraft meet, there will be interference drag, as not only is the wind hitting that sharp angle or that sticking out piece of metal, the wing strut, but the airflow going over the wing strut versus the airflow going under the wing, they meet together at a specific point, and that causes drag as it's turbulent airflow. However, parasitic drag goes is not as problematic at lower airspeeds, whereas induced drag is problematic at lower airspeeds. Parasitic drag becomes a problem at higher airspeeds, as there's more air pushing back on those imperfections, those surface meetings, and anything that's sticking out. Which brings us to our drag curve. Total drag is the sum of both the induced drag and the parasitic drag on an aircraft for any given airspeed, and is expressed as pounds. Drag itself is expressed as pounds. This drag curve also helps give us our Vy speed, or the speed at which an aircraft can fly the quickest with the least amount of drag. It's not usually a very quick speed, however, this is usually the speed that aircraft manufacturers give as a climb speed, as it makes it easier for an aircraft to climb when it's under the least amount of drag for a given flight configuration. This is the drag coefficient, or the equation that specifies what amount of drag you'll get for a given flight configuration, or for a given airspeed. CD is your drag coefficient, the amount of drag in pounds that the aircraft is experiencing at any given time. It is equal to the drag force, or the total force pulling back on an aircraft, divided by the reference area of the plane, or R in this case, which is times 1/2 of the plane's velocity squared. And as I said, this is expressed in pounds of drag. Something to note, induced drag can be eliminated at the lower airspeeds in a very specific situation. Induced drag is eliminated to almost zero when an aircraft is within one wingspan of the ground. This is because as the wingtip vortices are coming off the back of the wing, they don't have enough space to fully form off the wingtip. The plane is close enough to the ground that these wingtip vortices are disturbed by airflow on the ground that has nowhere to dissipate off to. Therefore, the wingtip vortices don't generate and dissipate before any lift is lost, which increases the amount of lift that the airplane is experiencing in that low, slow flight configuration, allowing a safer landing. It's also the reason why on most of the landings, right before you go to touchdown, the plane seems to fly a bit smoother and may also balloon. You're getting within that ground effect. Wingtip vortices and induced drag no longer have that major effect on your plane that they did just a moment before. But those are the major forces of flight. Like I said, flying is a very complex thing. At base level, it breaks down to the principles of weight, lift, thrust, and drag. They all act in opposition to one another. Weight opposes lift, thrust opposes drag. Thrust helps generate lift, and while weight doesn't necessarily help generate drag, it helps bring back an airplane. So weight and drag act against the aircraft, lift and thrust act with the aircraft, and these four forces are what allow us to have the amazing experience of flight. Thank you so very much, and have a good evening.